pedagogical picture, which I drew in a paper 40 years ago, which shows on a log plot upwards masses and along horizontally the radius. And it's a very extended scale, as you will see. Is there a pointer here? Yes. Oh, yes, yes, right. Yes, so you see here's a proton, and hydrogen atom there, and solid objects of ordinary densities, they're on a line of slope 3 in this log plot. This is the quantum uncertainty, Compton wavelength. This is a black hole line, slope 1 on the log diagram, and because gravity is so weak, a black hole, the radius of a proton, has a mass about 10 to 38 protons. And if you go up here, then we have solids, but when they get sufficiently big, gravity makes them round, and then when they get up to the scale of Jupiter, they start getting crushed, and we get into the domain of the stars. So, and I should say also that another important scale, which is important for quantum gravity, and maybe this is important for understanding of dark energy, this is the mass whose Schwarzschild radius is the same as Compton wavelength, the Planck scale here, 10 to the minus 5 grams, 10 to the 19 proton masses, and 10 to the minus 19 proton radii. So this encapsulates a lot of physics, and it's a nice pedagogical diagram. But I want to make 2 points. The first is that the fact that there's such a big scale between the micro world and objects where gravity is important, stars and planets, is because gravity is so weak. And indeed, if you were a theorist who've never seen a star, then the definition you might give of a star is the assemblage of that number, the gravitational fine structure constant to the minus 3 halves of baryons. There. About 10 to 57 baryons make up a star. Now, this is a slightly expanded picture, which anyone who's taught courses on stellar structure will know. It's just an expanded version of the top part of that picture, which is planets, Jupiter, neutron stars, radiation pressure dominating, etc. It's burning. But the point I want to make is that if you made G weaker, then you'd still get this pattern, but it would be on a much bigger mass scale. The number of baryons in a star would go as G to the minus 3 halves. And otherwise things would be fairly similar. So the main difference is that stars would be bigger, heavier, but you'd still have gravitationally bound fusion reactors, and they would live for much longer and last longer. And indeed, although it's not so obvious, if you had this universe where gravity was weaker, it would expand more slowly. One thing it would change is helium abundance, but galaxies would stay. They'd scale the same way, so the number of stars in a galaxy would be the same. So you could imagine a universe where gravity was, say, 10 times weaker, stars would be about 30 times heavier, galaxies 30 times heavier, and they'd live for longer. And this would be a perfectly good universe, so there's no particular fine-tuning in the gravitational constant. All we can say is that gravity must be very weak in order to have many powers of 10 between the scales of the micro-world and the scales where gravity is important. But the universe might be even more interesting if it was still weaker, because then you could have more time and more space. So, let me think about a second number, which is slightly more interesting. I mentioned that the fluctuations in the microwave background were about 10 to the minus 5. They're not simple, I showed that they differ on different scales, but this is a measure of the roughness of the universe, which is 10 to the minus 5. And this is normally a number called Q, which measures the smoothness. And this has a lot of effects. The gravitational binding energy of clusters of galaxies which eventually form is Q times their rest mass. So in our actual universe, where Q is 10 to the minus 5, a cluster of galaxies has a gravitational binding energy of 10 to the minus 5, so its velocity, dispersion, is the square root of that, which is about 1,000 kilometers per second, 1/300th the speed of light. And the maximum scale of the structures which are nonlinear in our universe now is again the square root of Q. So we can ask what would have happened if we had a universe where it was either smoother or rougher than our actual universe. Well, if it was completely smooth, of course, we'd now just have cold hydrogen, no stars, no galaxies, and no people. But if it was, say, 10 to the minus 6, not 10 to the minus 5, then galaxies would form later, they'd be less tightly bound, and probably they wouldn't form stars so efficiently. And below 10 to the minus 6, then you wouldn't really have any chance of having stars. So if you want to have a universe where stars and planets can form, then it can't be too smooth. Q must be at least 10 to the minus 6. But what about a universe where it's rougher than our present universe, say 10 to the minus 4 rather than 10 to the minus 5? This would actually be a rather more interesting universe than ours, because you then have structures forming earlier. And for instance, structures as big as a cluster of galaxies would condense out at a ratio of 10, and their gas would cool down because of Compton cooling on the micro background, and so you would have huge disk galaxies with a mass as big as a present cluster, and clusters would be still bigger. So this might be certainly a more interesting universe with a bigger range of structure. But if you go still further and have Q of 10 to the minus 3, then what would happen is that huge structures would condense out early on, and they collapse to be huge black holes. So you wouldn't have any galaxies. So what this means is that the range of Q, which allows a universe where stars and galaxies can exist, is not too narrow. Again, there's no fine-tuning, but it's between 10 to the minus 6 and about 10 to the minus 3. Suppose you had something even more than 10 to the minus 3. Then, of course, you have to rethink the idea of cosmology, because the idea of cosmology is based on assuming that we can treat the universe, obviously, as something which is smooth. So the structures are small compared to the overall scale. It's like an ocean, where even the biggest waves are small compared to the distance of the horizon. That's true of our universe now. But if Q was, say, 10 to the minus 2 or 10 to the minus 1, that wouldn't be true. It would be less like ocean waves than like a mountain landscape, where one big mountain could dominate the view. And so then we wouldn't really have cosmology, because cosmology is really distinct from astronomy, because we have a range of structures where we can talk about the average properties of the universe. But the point I want to make is that we have a range of Q. This again not tuned. Now what about the constraints on lambda, the cosmological constant? Then we know that it mustn't start to accelerate the universe too early before galaxies can form. And it can't be too negative, otherwise the universe will collapse too soon. So there's some tuning there. But if we imagine two or more parameters varying, then we realize that there is quite a big variety that's possible. And let me just take this case here, from where we have plotted along here the fluctuation amplitude, and up here the cosmological constant. Here, this is our universe, and as Steven Weinberg was the first to point out, the actual value of the cosmological constant is about a tenth of the maximum that will be allowed before galaxy formation was suppressed. But if Q is 10 to the minus 4, then you will be allowed to have a lambda 1,000 times higher, because things will condense out 10 times sooner. And so, if you consider two parameters varying, then the anthropically allowed space is very large, and you might ask, why are we here rather than there? We don't know. So, I want to argue that there isn't really very much fine-tuning, especially if you allow different parameters to vary and not just one. And let me now mention just a third counterfactual universe. Of course, we depend on complex chemistry, which means we need to have this binding energy diagram for the periodic table. And let's ask what would happen if we didn't have that. Of course, the periodic table and nuclear fusion is crucial for stars, and that's why we have the whole idea of stellar evolution, where we can calculate, we've known for many years, how stars evolve depending on their masses and leave different remnants. And we know that the process of stellar evolution leads to the formation of the atoms of the periodic table, because a massive star, before it dies, has this sort of onion skin structure. When it explodes as supernova, this goes out into space and mixes with interstellar gas, and new stars form in this way. And it was in fact in the late 50s that these four people, Geoffrey and Margaret Burbidge, Willie Fowler and Fred Hoyle, really codified this idea, or the essence of it. And this showed how you could understand the production of the elements, and roughly speaking the proportion of them, the abundance as a function of atomic number. This was fine up to iron. The high numbers, the high, much heavier elements, they are more difficult to explain, and of course there's been some recent excitement that binding neutron stars, only just discovered to be coalescing, these can be perhaps the origin for elements like gold, which couldn't be explained very well by these four people. But a number of authors recently, in particular Fred Adams at Michigan, they've tried to see how sensitive the production of elements is to particular nuclear constants. If you vary the mass of the electron or the strong interaction, cross strength, etc., what changes? I won't go into that, but I thought I would mention something about a very extreme case, what I call the nuclear-free universe. This is a universe where you assume there's no strong interaction, or at least no sufficiently strong one, to allow anything other than protons to exist. There you just have hydrogen, but nothing else. And it's interesting that this would give you a universe that, in outward appearance, would not differ very much from our universe. Because stars would still form, and they would contract, but whereas a normal star contracts until nuclear fusion switches on, these would go on contracting until they became white dwarfs, and then they'd stop. And for a pure hydrogen star, the Chandrasekhar limit is 5.5 solar masses, so all stars less than that, they would go on radiating until they became white dwarfs. More massive stars, they would go on contracting to become black holes. And in fact, this universe might be quite bright, because you released off energy going down to white dwarf size, and in making a black hole, you might release even more energy than is released in a normal massive star supernova. So, if you looked at this universe, you'd have galaxies, rather like in our present universe, and you'd have stars and Jupiter-like planets, and the universe would not be much fainter than our actual universe. But of course, you'd have no chemistry, no rocky planets, no life. So it would resemble our actual universe, only in the sense that a marble statue resembles an actual human being. It would look the same in outward form, but would have no internal complexity. Maybe one exception will be, anyone who's read Fred Hoyle's book, The Black Cloud, you could have that as a complex intelligence in a pure hydrogen universe, but unless you have that, then this would be a sort of sterile universe. So, we can imagine a range of universes with different parameters and different combinations. And the main point of what I've said is that obviously some would be sterile or stillborn, but there's quite a wide range of universes which would be very different from ours, but would still in principle allow complexity. And some could be even better, in particular the universe with larger fluctuations, or universe with a weaker gravity. But as I said, again, for those whose minds are close to the multiverse concept, this is just an exercise in counterfactual history. And of course, anthropic arguments are irrelevant if the constants are unique. Otherwise, they're the best explanation we'll ever have. And let me illustrate this by another historical throwback back to Kepler. Kepler thought that the orbits of the planets were governed by beautiful mathematics, the nested platonic solids. We, of course, realize there's nothing fundamental about the orbits of the planets. They're historical accidents, and our planet is just one which is in the anthropic range. It's around a stable star, and it's at the right temperature for water to exist. We don't expect any fundamental formula to determine the orbits of planets. If string theories arise or made different vacua, etc., then we will have to abandon any hope of getting precise exact formulae for the fundamental constants. And some don't like the concept simply because it would render the hope for neat explanations of fundamental physics numbers just as vain as Kepler's numerological quest to understand the solar system. But our preferences are irrelevant to the way physical reality actually is. So we should, in my view, be open-minded about the possibility of a fourth and grandest Copernican revolution. We've had the Copernican revolution itself, then the realization that there were zillions of planetary systems in our galaxy, then there were zillions of galaxies in our observable universe. But we then realize that our observable domain is just a tiny part of some far larger and possibly diverse ensemble. So we would live not in a typical part of the multiverse, but a typical domain in the subset, which allows complexity to evolve. And the question is this really a scientific question or not? Some people say, well, we can never observe these other space-times, so it's not part of science. I don't think that's fair, because we can perhaps gain confidence in a theory which predicts them, and then we believe this prediction. Let me give an example. Andre Linde's eternal inflation is well worked out, and it works if the physics of 10 to 16 GeV has particular properties. We don't know if it does have those properties. But we may have a unified theory which does apply to the inflation era, and which is tested by being vindicated in our low energy world. It might be a theory which is able to tell us why there are three kinds of neutrinos, or what the masses are, things of that kind. So if we had a theory which was vindicated and which applied at the inflation era, then we would take seriously its implications about what happened in inflation. And if it had the properties leading to a multiverse, then we should take that seriously. To give another analogy, we take seriously what Einstein's theory says about the inside of black holes, even though we can't observe them, because we've gained confidence in the theory by being able to observe its validity in many contexts outside. So it's not true you have to be able to test or observe every consequence of the theory. You have to be able to test the theory enough to gain confidence in it, and then you believe it even when you can't test it. And this, I think, is going to be the situation for the multiverse. If we have a theory which we gain confidence in, then we'll be able to ask, what does it imply for the very early universe at these ultra-high energies, and maybe it will apply to a multiverse. And, of course, if we want to ask, are we in a typical universe, then we have to open another can of worms and ask about the measure of probability about different values of the constant. Well, in fact, about 10 years ago, I was on a panel at Stanford where we were asked by the chairman, who is Bob Kirshner, an astronomer, how much we'd bet on the multiverse concept. On the scale, would you bet your goldfish, your dog, or your life? And I said I was almost at the dog level. Andre Linde, who had spent 25 years working on the inflationary model, he said he'd almost bet his life. And later on being told this, the great theorist Steven Weinberg, he said he'd happily bet Martin Rees's dog and Andre Linde's life. Well, Andre Linde, my dog, and I will all be dead long before this is settled, but I would make the point it's not necessarily metaphysics. It's highly speculative, but it's exciting science, and it may be true, and we would be able to test whether it's true if we had a theory which applied at these very, very high energies. Well, just to finish with, and returning closer to less speculative matters, I realize that I'm speaking in the World Centre for Computational Astrophysics, so I thought I would make the point that up till now, progress in cosmology and high-energy astrophysics has been owed 95% to advancing instruments and technology, less than 5% to armchair theory. And the one thing that's changing that balance is computer simulations, which have hugely advanced in power and expanded in scope. That's certainly true in studying the expanding universe. It's also been true, as we know, for strong field general relativity. We are able to calculate the gravitational waves from merging black holes, and this calculation was fortunately done before the data came in. We can have relativistic MHD calculations to study the flow around black holes, and we can study supernova explosion without spectrosymmetry, and we can study plasma microphysics to understand shocks and acceleration, etc. And this, I think, is very exciting, and the computational work is certainly taking over, especially as a subject where we can't directly do experiments. And I think this is what we can look forward to in the future. And just finally, the 1960s, when the subject opened up, they were exhilarating for young astrophysicists at that time, because there was so much new that the old guys didn't have a big head start. But I'm not here to be nostalgic, and indeed there are some students and postdocs here, and I want to emphasize that today is an even better time for young researchers. The pace of advance has crescendoed and not slackened. Instrumentation and computer power have improved hugely. And on that encouraging note, I would conclude with a quote from Edwin Hubble. He is heavy smoker, as you can see, and he said in his book Where Were the Nebulae, only when empirical sources are exhausted should we enter the dreamy realm of speculation. So let me end with that thought, and with a nice computer simulation of the present structure of our universe. Thank you very much for listening.
I'm happy to be here today to talk about Titan and the Dragonfly mission concept that we've been working on for the past few years. I studied Titan for the better part of two decades at this point. I started studying Titan as part of the Cassini team, working with the Cassini cameras, the imaging science subsystem, and planning the observations of Titan with the cameras, and then also worked with the Cassini radar instrument as well. So it's been a real privilege to be able to explore this place that used to be such a mystery and has become so familiar to all of us through Cassini's exploration. And I am now the principal investigator of the Dragonfly mission concept, This is a mission that we've proposed to New Frontiers. That's the same program under which the Juno mission that's currently operating at Jupiter, the OSIRIS-REx mission that just got to the asteroid Bennu, and the New Horizons mission that just flew by MU-69 in the distant reaches of the outer solar system. This is the same program that those missions have flown under. At this point, we are in the last part of the competition. 2 missions were down-selected from the first group that were proposed, and those 2 missions have had another year of study, and we're coming up on our site visits, which is the last part of the last step in the competitive process, and NASA will be making a decision on what mission to fly sometime this summer. So hopefully we'll be able to fly. So Titan is one of the moons of the planet Saturn. You can see, this is a natural light. This is what Titan would look like to our eyes. There is. Thank you. Thank you. I also can use this one, if I get it right. There we go. Yes. So there's Titan has an atmosphere. I'll talk about that a little more. And at visible wavelengths, the haze in the atmosphere obscures the surface. So Titan has been quite a mystery up until recent times. So why do we want to go to Titan? We don't know how life came to form on Earth. And we can't study the prebiotic chemistry on Earth because it's all overprinted with all of our biology. So we look to other places in the solar system that provide pieces to the puzzle of how the chemical processes that led to the development of life. And Titan, chemically, is the most like the early Earth. It's the place in the solar system that offers us the same chemical building blocks that were available on the early Earth. So it holds keys to understanding our chemical origins. So here's Titan, again. It's the largest of Saturn's 62 moons, and not only does it stand out, of course, because of its size, it stands early in the 20th century. Hints in observations suggested just after the turn of the century that there might actually be an atmosphere at Titan, and that was confirmed by detecting methane in the spectrum of Titan in the 40s. So it is not only unique within, as I said, the Saturnian system, but it's unique within the, if I can find the pointer, there we go. There we go. It's unique within the other satellites in the solar system. So these are its cousins, the Jovian satellites up here, the Galilean satellites at Jupiter, and of course our moon, and Neptune's moon Triton. These are all to scale. Again, there's a lot of variety in the outer solar system, or in the solar system in general. It's a fascinating place, but again, Titan stands out because it has this atmosphere. But this doesn't just make it unique among all the satellites, it makes it unique among planets as well, among the worlds in our solar system. Again, these are all shown to scale. Titan's atmosphere is actually the second densest in our solar system after Venus. It's denser than our atmosphere here on Earth, and the surface pressure on Titan is actually 1.5 times the surface pressure here on Earth. So it actually has, it's a world unto itself in this sense. And you can see here, it's actually just between Mars and Mercury in size. Another thing that's large about Titan is its year. Saturn's orbit around the Sun takes 29.5 Earth years. And in that time, the Saturnian system is tilted. It's actually tilted a little more than the Earth is. And so in that time, you can see at the top here, the way the rings, this is what Saturn would look like from Earth, over its year. So the rings open and close, and with it, the entire satellite system go through the same kind of pattern, the same seasons that we have here on Earth. Except you can see that the seasons on Titan are much longer. So the northern winter solstice was in October of 2002, the equinox in 2009, and we just passed the northern summer solstice in 2017. So it's a very extended season, but nonetheless a fascinating process that gives it another aspect of Titan that's very Earth-like. Titan's day is actually 16 days long. It's tidally locked to Saturn, so the same face of Titan always faces Saturn, and it takes 16 days to orbit Saturn. So the same side of Titan always faces Saturn, like our moon. There is a small tide on Saturn, but Titan is much smaller than Saturn. But like our moon, so Titan and Saturn, it's the same, similar to the tides on Earth. There is not, but the atmosphere will move the same way that our atmosphere moves. The chemical composition of Saturn is gaseous. It's gaseous in the atmosphere, so there. Yeah.
Why don't we wait to the upper one?
That's okay. So I wanted to put the exploration of Saturn and Titan in the context of the year, of Saturn and Titan's year. So this again just shows the year starting from we'll start from the winter solstice, running through the northern vernal equinox, the summer solstice. The exploration of the Saturn system by Pioneer and the 2 Voyagers was around the northern vernal equinox in Titan's year. And the Cassini spacecraft got there, arrived at Saturn in the summer of 2004, and the Huygens probe explored Titan in the early part of 2005. So this was actually just after the winter solstice. Cassini, the spacecraft, was operating well, and so the mission was extended through the equinox. So we call that the Cassini equinox mission, extended through the northern vernal equinox. And the spacecraft was still healthy, still functioning well. So there was another mission extension. So Cassini all told spent 13 years in the Saturnian system, which is a good portion of a Titan and Saturnian year. So that was really valuable in order to understand Titan as a system. And so the solstice mission took Cassini all the way through the summer solstice in May 2017, a few months later, before the end of the mission. So this is our view of Titan as of the Voyager 2 observations. It wasn't until the 90s that we finally got a glimpse of what was underneath the haze. I'll actually take that back. It turns out Voyager did detect the surface, but you had to know what the surface looked like to prove that it saw the surface. So we technically did see the surface with Voyager, but we didn't know it until we saw the surface with other detectors. So the Hubble Space Telescope, looking at Titan out in the infrared, made the first map of brightness on the surface of Titan. And later on, as adaptive optics improved, we got other images of the surface, maps building up of the surface. So we saw finally that there were bright areas and dark areas on the surface of Titan. So this was important because it wasn't known at the time whether the surface might be covered with a liquid methane ocean, whether it might actually not have land features at all. So the fact that we saw the same features, that they were stable from time to time, suggested that there were indeed land features on the surface of Titan. So the Cassini spacecraft and the Huygens probe